No matter where you are on Earth right now, there's approximately 6,400 kilometers or 4,000 miles of rock between you and the center of the Earth. All of that rock isn't the same. There exist different layers below the surface that have different properties and different compositions. There's even a layer near the center of the Earth when the rock isn't even a solid, but it's a liquid. And the way we're able to know what lies beneath the surface is one of the greatest accomplishments of science. Learn more about the composition and interior of the Earth on this episode of Everything Everywhere Daily.
Right now, the Home Depot has spring deals under $20. So what are you working on? If you're planning on cooking out this season, head to the Home Depot so you can fire up the grill with deals on charcoal. Right now, get two 16-pound bags of Kingsford charcoal for only $17.88. Was $19.98. Don't miss spring deals under $20 now through May 7th at the Home Depot. Subject to availability, valid on select items only.
Find mom's best gift at Target. Now through Mother's Day, get up to 40% off gifts for her. Discover trendy apparel and swimwear that'll elevate any wardrobe. Jewelry that'll make her smile shine brighter, and even chocolate that'll turn any moment into something sweeter. There are endless options to choose from to show her she's the best. Hurry! Save 20 to 40% on select apparel, jewelry, chocolates, and more this Mother's Day only at Target. Restrictions apply.
From the scale of a human being, the Earth is enormous. I've been all over the world and I've circumnavigated it several times, but I've only scratched the surface of the surface. Despite the fact that everything we have ever made, seen, and explored has been on the surface, the vast, vast majority of our planet lies beneath our feet. However, we can't observe it directly. If you remember back to a previous episode, the deepest hole ever made was the Kola Super Deep borehole in Russia, which reached a depth of 40,230 feet or 12,262 meters. The Soviets drilled the hole just to see how deep they could drill a hole and ended the project in 1989. While the Kola borehole was indeed very deep, in the big scheme of things, it was nothing. It didn't even break the Earth's crust and was only about 0.2% of the way to the center of the Earth. If we've never drilled down any further than that, and in fact it would probably be impossible to go much further than that, how in the world do we know so much about the interior of the Earth? So before I get into what the interior of the Earth consists of, I should address how we know what we know. There are multiple techniques that geologists use to piece together the puzzle of what the interior of the planet is like. The most important tool by far are seismic waves. Whenever an earthquake occurs around the world, and there's at least a few small earthquakes every day, seismographs around the world can measure the seismic waves produced by these earthquakes and infer what's inside the Earth. There are two different types of seismic waves that travel through the planet. The first is a P wave. A P wave, or a primary wave, is a type of seismic wave that compresses and expands material in the direction it travels, moving fastest through the Earth and capable of passing through solids, liquids, and gases. Imagine a slinky toy where you push on one end of it. That would be a P wave. The other type of wave is an S wave. An S wave, or secondary wave, is a seismic wave that moves material perpendicular to its direction of travel, creating a shearing motion, and can only propagate through solids. In the case of a slinky, imagine you moved it up and down to create a sine-like S-shaped wave. That's an S wave. P and S waves change speed and direction when passing through different materials. By measuring how long they take to arrive at a seismic station around the world, geologists can infer the density and phase, that being whether it's a liquid or solid, of the materials it passes through. However, P and S waves do not behave the same. S waves cannot pass through liquids, so the disappearance of S waves beyond certain distances reveals the presence of liquids inside the Earth. Sudden changes in wave velocities can also mark layer boundaries. Over time, by analyzing thousands of these seismic waves through the Earth, Geologists can determine where these waves were recorded and where they originated to create a map of the various layers inside the Earth. Depending on the angle from the origin of the earthquake, there are shadow zones on the Earth that do not receive seismic waves. Seismic waves can tell us the rough density and composition of the interior of the Earth, but they can't tell us much about its chemistry. For that, we have to recreate the conditions deep inside the Earth in a laboratory. Scientists simulate the high-pressure, high-temperature conditions of Earth's interior by using diamond anvil cells and high-temperature furnaces. By compressing known materials under extreme conditions, they observe how minerals behave and transform, mirroring what happens inside the Earth. They identify which mineral phases should exist at certain depths, which is how we can infer what is sitting below our feet. There are other clues we can use to infer what is inside too. Meteorites are believed to be fragments of early planetary material, similar in composition to Earth's building blocks. Iron meteorites suggest what the Earth's core is made of. Stony meteorites resemble the mantle and crust composition. Small variation in the Earth's gravity reveals density differences in the crust and the mantle. And all of this data can be pieced together to create theories of what is inside the Earth. So with that, let's start moving down towards the center of the Earth, and we'll start with the layer which is immediately beneath us, the crust. The crust is the Earth's outermost solid layer, comprising of less than 1% of the Earth's volume. It's relatively thin and rigid, floating on the more ductile and malleable upper mantle. There are generally two different types of crust: continental crust and oceanic crust. Continental crust thickness ranges from about 30 to 70 kilometers, depending on the location. Oceanic crust thickness ranges from 5 to 10 kilometers and is found at the bottom of the sea. The biggest difference between the two is their composition and density. Continental crust has an average density of approximately 2.7 grams per cubic centimeter, whereas oceanic crust has an approximate density of 3 grams per cubic centimeter. Continental crust is also much older, being billions of years old in some places, whereas oceanic crust is much younger and is being constantly recycled via plate tectonics. In areas like the Mid-Atlantic Rift, new oceanic crust is being created, and in places like the Ring of Fire along the Pacific Ocean, it's being subducted underneath lighter continental plates. Below the crust is the mantle. The mantle is made of several different layers. The mantle comprises about 84% of the Earth's volume and extends down to about 2,900 kilometers deep. The first part of the mantle is the upper mantle. The lithospheric mantle and the asthenosphere are two key sublayers of the upper mantle, which extends from the base of the Earth's crust to about 660 kilometers deep. The lithospheric mantle lies just beneath the crust, and together with it forms the rigid outer shell of the Earth known as the lithosphere. This layer is solid, relatively cool and brittle, and is broken into tectonic plates that move over time. Below the lithosphere is the asthenosphere, a ductile, partially molten region that extends from about 100 to 250 kilometers beneath the surface. The asthenosphere is solid rock, but due to higher temperatures and pressures, it behaves plastically and can flow slowly over geologic timescales. This flow allows plate tectonics to move on top of it, making the asthenosphere a crucial zone for both plate tectonics and mantle heat convection. Though both are part of the upper mantle, the lithospheric mantle is mechanically rigid, while the asthenosphere is weak and deformable. Below the upper mantle is the transition zone. The transition zone is a distinct region within the Earth's mantle located approximately 410 to 660 kilometers beneath the surface, and that marks a major shift in mineral structure due to increasing pressure and temperature. Rather than being a compositional boundary, it's defined by changes in the crystal structure of mantle minerals, particularly the transformation of the mineral olivine, which is dominant in the upper mantle, into denser forms such as wadsleyite and ringwoodite. Olivine is very rare on the surface of the Earth, and it's better known in its gemstone form as peridot. You can find olivine in small green flecks in volcanic rock in the Big Island of Hawaii, for example. Wadsleyite and then ringwoodite are chemically the same as olivine. They simply have different crystal structures at the pressure and temperatures that they're found at. For geologists, a different crystal structure constitutes a different phase. These phase changes result in a significant increase in density and seismic wave velocity, which is why the transition zone is readily identifiable in seismic data. The region acts as a barrier or filter for mantle convection, with some plumes and materials able to pass through while others are trapped above or below. The presence of water-bearing minerals in this zone also suggests that it may play a role in deep Earth water cycling. The lower mantle, also known as the mesosphere, extends from the base of the transition zone at about 660 kilometers to the core mantle boundary at about 2,890 kilometers in depth, making it the thickest layer of the Earth's interior. Unlike the more deformable asthenosphere above, the lower mantle is composed of dense, solid rock that behaves as a very slow-flowing solid over long timescales. Temperatures in the lower mantle rise from about 2,000 degrees Celsius to 3,700 degrees Celsius, yet the rock remains solid due to the crushing pressure. This layer is crucial in mantle convection, as it transmits heat from the deep interior towards the surface, powering plate tectonics and volcanic activity. Seismic waves travel more quickly through the lower mantle than through the upper mantle, indicating its rigidity and uniformity, though recent research suggests that it may contain compositional layers and variations, particularly as it gets closer to the core. Below the mantle is the core, and here things really change. The outer core is a liquid layer of the Earth located between the lower mantle and the inner core, spanning depths from about 2,890 to 5,150 kilometers below the surface. Composed primarily of molten iron and nickel, along with lighter elements such as sulfur and oxygen, it has a density ranging from approximately 9.9 to 12.2 grams per cubic centimeter. Temperatures in the outer core reach between 4,000 degrees Celsius and 6,000 degrees Celsius, which is hot enough to keep its metallic components in a liquid state despite the immense pressure. This liquid metal is in a constant convective motion, driven by heat escaping from the inner core and the cooling of the Earth, and these movements generate electric currents. These currents are responsible for the Earth's magnetic field through a process known as the geodynamo. One of the most significant pieces of evidence for the outer core's liquid state is the absence of S-waves in this region. S-waves cannot travel through liquids, resulting in a well-defined seismic shadow zone. The outer core plays a vital role not only in geodynamics, but also in shielding the planet from harmful solar and cosmic radiation via the magnetic field it helps sustain. The final part of the interior of the Earth is the inner core. The inner core is the solid innermost layer of the Earth, extending from about 5,150 kilometers to 6,371 kilometers beneath the surface. Despite the extreme temperatures, estimated to be as high as 6,500 degrees Celsius, the inner core remains solid due to the immense pressure from the overlying layers, which prevents the nickel-iron alloy that composes it from melting. Interestingly, the inner core is believed to rotate slightly faster than the rest of the planet and exhibits seismic anisotropy, meaning seismic waves travel faster along certain directions, indicating that it has a crystalline structure aligned with the Earth's rotation. The inner core grows slowly over time as the outer core cools and iron crystallizes into it, and this solidification process is a key driver of the convection in the outer core that sustains the Earth's magnetic field. I'd like to end the episode by addressing a major question that some of you might have. Why is the interior of the Earth so hot? There are two major sources of heat. The first is residual heat from the formation of the planet over 4 billion years ago. When the Earth formed, it involved many violent collisions which produced a lot of heat. Some of that heat is still trapped in the planet as it takes so long to get to the surface. However, the primary source of all the heat inside the Earth is radioactive decay. Radioactive isotopes have slowly decayed since the formation of the Earth, and the heat which was created in the process has mostly remained trapped. So, in a very real sense, geothermal power is just nuclear power with some added steps. So it might not seem like it, but beneath your feet is thousands of miles of rock, and geologists have figured out how it works without ever having touched it or even seen it. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Austin Oakton and Cameron Kiefer. I want to thank everyone who supports the show over on Patreon. Your support helps make this podcast possible. I'd also like to thank all the members of the Everything Everywhere community who are active on the Facebook group and the Discord server. If you'd like to join in the discussion, there are links to both in the show notes. And as always, if you leave a review or send me a boostagram, you too can have it read on the show.